Hello and welcome to this next video about derivatives. In this video we're going to talk about the derivatives of the exponential function and also of the logarithm as the inverse of the exponential function. So this is called derivatives of exponential function and logarithm. So recall our definition of the exponential function first. Remember, we defined the exponential function, or e to the power of x, through a limit process, more precisely as the limit of 1 plus x over n to the power of n for n to infinity. So the limit of the Euler sequence. And from this definition, we'd like to infer that the function indeed is differentiable. And we'd also, of course, like to know about the derivative of the exponential function. As it turns out, and that's the central theorem of this section, the derivative of the exponential function is the exponential function itself. So the exponential function exp, which is defined on the reals and maps to the reals, is differentiable on the whole real line with exp prime of x equals exp of x. And in the following, I'd like to prove to you that this is actually true. Now, the main idea of this proof is to use this definition here and apply the sandwich theorem in a clever way to then be able to derive the necessary limit of those limits for the derivative. First, I'd like to establish an inequality that holds more general, and then I'd like to use this inequality and apply that to the special case that then yields a function defined by that limit, so that we can finally find the correct derivative of the exponential function this way. So we start with a more general statement, and that is, consider AB, two numbers in R with A less or equal to B, and both numbers non-negative, and consider them some n in n, the natural numbers. Then we have the following equation that holds: b to the n minus a to the n equals b minus a times b to the n minus 1 plus b to the n minus 2a plus b to the n minus 3a squared, and so on, up to b a to the n minus 2 plus a to the n minus 1. You can just multiply those two factors here to see that the statement is actually true. And of course, if you've watched other videos as well, you might recall that from earlier implementations of that same formula. So we have in total n factors here. And in particular, this implies two inequalities. The first inequality is about to b to the n minus a to the n from below. So I'd like to establish that one first. And that comes from the fact that a is less or equal to b. Now if a is less or equal to b, of course that implies if we replace every occurrence of b here by an a, then the whole sum decreases, or at least does not increase. So what that means is, if we do this, we get, instead of the b's, we get a, so we get a to the n minus 1, we get a to the n minus 2 times a, which is again a to the n minus 1, and so on. So we get n times the same factor, a to the n minus 1. And this is less or equal to this. So what we get, if we do this, is we get this b minus a, this factor, we don't change that one, times n times a to the n minus 1. And this is less or equal to b to the n minus a to the n. And on the other hand, if we replace every occurrence of a in this formula by b, then we increase the sum because b is greater or equal to a. And if we do that, again, we get n factors of the same type, and this time it's b to the n minus 1. So the right-hand side, the upper bound here is b minus a times n times b to the n minus 1. And this is the inequality that we're going to use. Now we're going to apply this inequality, and we're going to apply it to special choices of a and b. Specifically, for x greater or equal to 0, we choose a is 1 plus x over n, and we choose b is 1 plus x plus h over n for positive h. And it will turn out we don't even need that this is greater or equal to 0. So we can just leave that out. If the only thing that we have to make sure is if we choose the n large enough. And large enough means we're going to assume that n is greater than x, or greater than the absolute value of x. Because if that is the case, then this factor here is smaller than 1 in absolute values, or greater than minus 1 if x is negative, and that means a is still non-negative, and the same is true for b because we assume h to be positive. Okay, so if we choose this, then b minus a, where if we take b and subtract a, and we subtract 1, minus 1, and here we have x over n minus x over n. What remains is h over n. So this difference is equal to h over n. And thus we get the following from our inequality here. So we now take these two inequalities here, and remember b minus a is h over n, so this becomes h over n times n times a to the n minus 1, and a is 1 plus x over n, so this to the power of n minus 1. Now this is less or equal to b to the n minus a to the n. So b to the n is 1 plus x plus h over n to the n minus a to the n, 1 plus x over n to the n. And on the right-hand side here, we get, again, b minus a, which is h over n. And then we have n times b to the power of n minus 1. So times n times 1 plus x plus h over n to the power of n minus 1. So this is what the inequalities here provide. And what we'd like to do now is, of course, we'd like to take the limit as n approaches infinity, so that hopefully these expressions here will have something to do with the exponential function, and these here as well. Of course, this is not exactly the limit that we need, right? You'll see that here we have an n, here we have an n minus 1. Originally, what we need is an n here and an n here. So let's have a look at that limit here first. So we want to compute that limit as n tends to infinity of 1 plus x over n to the power of n minus 1. And the trick here is pretty simple. What we want to do is we want to write this as 1 plus x over n to the power of n. And of course, we cannot just do that. We have to divide by this factor here to be able to do that, or multiply by the reverse, and that's exactly what we're doing. So this is the same as n plus x over n. So we divide by that factor, and that means we multiply with n over n plus x. So this is the same expression now. And now if we want to compute this limit, well, what we get here is, again, 1 plus x over n to the power of n times, and this here is equal to 1 over 1 plus x over n. Now x is fixed, and n tends to infinity, so if n tends to infinity, then this here tends to 0, and that means this whole expression here, that will tend to 1. And we already know what this is. This will tend to the exponential function at x. So the little change here does not really matter. Doesn't matter whether we have n or n minus 1. In the limit, it's still going to be the exponential function e to the power of x, or x of x. Of course, the same idea can also be applied to this function here. So that doesn't really make a difference whether we have this plus h or not. We'll get x of x plus h instead of just x of x. And that means what we obtain from this chain of inequalities here will be the following. Let's copy that first so we can have a look at the inequalities separately. So here's our chain of inequalities once again. And what we can do now is, if n goes to infinity, then of course, first thing to notice, the n here cancels out, and the n here cancels out as well. So those don't matter. What matters is, of course, this expression here. And we just seen as n goes to infinity, this goes to exp of x. So we have h times exp of x here, less or equal to. The same works here in the middle. We have this expression minus this expression. And those are exactly the Euler sequences. So what we get here is, as n tends to infinity, this is exactly the exponential function at x plus h. And this is the exponential function at x. And finally, on the right-hand side, again, the n cancels out, and we're left with h times the exponential function of x plus h. And again, this all holds as n tends to infinity. Now, what can we learn from this? Well, the rest is simple. We just have to divide this whole thing by h. And if we do that, we obtain x above x is less or equal to x above x plus h minus x of x divided by h is less or equal to x of x plus h. And now we apply the sandwich theorem and let h tend to 0. So if we do that, next step, take the limit as h goes to 0. What we get then is, well, this here doesn't change. We still have x by x. It doesn't depend on h. This right bound here, this tends to x of x, of course. And this middle thing, this middle bound here, we can then conclude that the limit in the middle exists and is equal to those two values here, because the expression in the middle is sandwiched between those two. So the conclusion here is the limit of x plus h minus x over h for h to 0 does exist and is equal to the exponential function at x. And this limit, of course, is exactly the derivative of the exponential function. So this proves that the derivative of the exponential function is indeed the exponential function itself. Now, precisely speaking, we only have argued that for h positive. Of course, you can make the reasoning in a very similar way for negative h, and the outcome will be the same. So let's just add this as a quick note here. The reasoning for h negative is very similar. And this completes the proof. So we have actually seen that the derivative of the exponential function is the exponential function itself. And the proof is an application of the sandwich theorem. Now, of course, we'd also like to discuss the logarithm, which is the inverse of the exponential function. And we also know a theorem that tells us something about the derivative of the inverse. So hopefully that should be easy if we just apply that theorem. And indeed, let's write down the result. Indeed, what happens here is if we define the logarithm, the ln, to be the logarithm to base e, and this is exactly the inverse of this exponential function. So what we'll do is we'll say let ln be the logarithm to base e, like this. And then this function ln is defined on the interval from 0 to infinity. Open interval from 0 to infinity. And this is the inverse function to the exponential function. And of course, if we write it in this way, the domain of the exponential function is always r, but the codomain will then have to be restricted to 0 infinity through the open interval 0 to infinity, because otherwise the function wouldn't be bijective. But if we restrict it in this way, then these two are inverse to each other. So we can apply the theorem about the inverse of a function and its derivative. And if we do that, and I'll do that in just a second, we find out that its derivative is ln prime of x is 1 divided by x. Now let me just show you very quickly how you can derive this result. By using this theorem about the differential derivative of the inverse, we can say this is the same as 1 over the derivative of the original function exp at ln x. Now, knowing that the derivative of exp is the function itself, well, this is the same as the exponential function at ln x, and of course, as the exponential function and the ln are inverse functions, that means x of ln is just x once again. So this is how you get this result very quickly once you have the strong theorems in place that we've discussed. And finally, we can use these relations here to define and to also differentiate functions based on the idea of this exponential function and the logarithm. So this is the last theorem for this video here. And this is about generalized exponential functions. So the first function we look at is if we fix some real number lambda, for lambda in R, we can define a function x to the power of lambda. Before, we basically only defined x to the power of lambda for integer lambda, and then we extended that to rational lambda. Remember, we had the notation that the nth root is something like x to the power of 1 over n, and now we extend that to arbitrary real numbers, not just rational numbers. And the extension is actually pretty easy. Now this is a function defined on the interval from 0 to infinity and mapping to the interval from 0 to infinity, and is defined as x to the power of lambda is simply the exponential function of the ln of x to lambda using the laws of logarithms. We can reformulate that to read like lambda times ln x, right? Remember, this here is the same thing as the exponential function of ln x to the power of lambda. Obviously, the exponential function of the ln is the same as the argument, so this is x to the power of lambda, and this motivates this definition. So this works for every rational lambda, and we can, of course, with this definition, just extend that to arbitrary real numbers lambda. So this is the definition of arbitrary powers, arbitrary real valued powers. And this function is differentiable. And the derivative is ddx, x to the power of lambda, is simply lambda times x to the power of lambda minus 1. So all the rules for taking derivatives of that kind with a constant lambda and a variable x also work for general real numbers lambda. So this is the first generalization here. The second generalization is to allow for arbitrary bases. And what we want is the base, we want it to be positive so that we avoid problems with a sign. Of course, we can also allow negative bases if we generalize this in some other way. But for now, let's stick to the positive basis to avoid the technicalities involved here. So for a strictly positive, we can then define a function, a generalized exponential function, a to the power of x. So this time a is constant, the basis is constant, and the power, the exponent, is x, the variable. So this is a function defined for arbitrary real values of x. And it's defined as a to the power of x is, in the same way as before, exp of x times ln a. You can see now why we wanted a to be positive, because that avoids technical difficulties with the ln. One can solve that for most a's, not for all a's, but for most a's in some way, but we're not going to bother with that. Again, that function is differentiable. And the derivative is ddx of a to the power of x is a to the power of x times ln a. And of course, you can just derive that from the derivatives of ln and of the exponential function using chain rule and product rule and things like that. So if you just compute that derivative, you should get that result. So it's similar to the exponential function itself. It also reproduces, as you can see. So ax, that's here again. But it also produces an additional factor, ln of a. And of course, if you choose the a as e, as Euler's number, then ln of e will be 1, and that vanishes. So this is kind of the special rule that Euler's number plays here. The exponential function defined with e as its base is the one where the derivative is equal to the function itself. Okay, for the proof of these two results, you just do the computations. I'm going to spare you with that here in the video, but of course you're welcome to try this at home and practice applying differentiation rules to these functions yourself. So that concludes this treatment of the exponential function, the logarithm, and their derivatives, so that we can now also use those. And in the following videos, as you might have imagined, I'm going to talk about derivatives and their applications a little more. So as usual, I hope I'll see you then.